All right. Good morning from my time, everyone. So today we have the pleasure of, I have the pleasure of introducing Christian Sampson, who is a project scientist working on the JEDI project at the Joint Center for Satellite Data Assimilation in Boulder, Colorado. Before that, he was a postdoc in mathematics at UNC Chapel Hill, where he was introduced to data assimilation, working on new methods for adapting mesh models in the context of sea ice modeling. Today, he will be talking about predicting the weather, 4D VAR, hybrid tangent linear models, and JEDI. Okay, so go ahead, Christian. You may go ahead and get started.
Great, yeah. Thanks, Emmanuel, for the introduction, and thanks for the invitation to talk. So yeah, as Emmanuel said, I'll just talk a little bit about weather prediction in general, how it's done, show some examples. 4D VAR, which is a data assimilation method that typically produces the best forecasts today. Hybrid tangent linear models, which tie into 4D VAR and easing the burden of coding on 4D VAR. And then I'll talk about the JEDI project a little bit, what it is, how people could be involved as well, because it's certainly an open project that we want lots of people to contribute to. What is numerical weather prediction? Well, it's exactly what it sounds like. We solve a bunch of equations numerically to try to predict the weather. So typically, if you can see my mouse, we have a digital copy of the Earth, including some of the physics, pressure, temperature, humidity, heat fluxes, radiation fluxes, anything that you could think of. But it's a discrete model of the Earth with many vertical layers. They'll all communicate to each other. There's a lot of physics parameterizations within these subgrids, but as best as we can do with the computational power we have a digital copy of the Earth that we run. This is our model, but it's not just the model that we use to try to predict the weather, because models are imperfect. We also use a lot of data. So this is just a little animation of some of NASA's Earth observing satellites, for example. The ESA has satellites as well. There's other observations that get brought in: weather radar, airborne measurements, shipborne measurements, just temperature monitoring stations on the ground, data coming from all sorts of sources. That goes into these weather predictions too. And the process by which that happens is essentially data assimilation. The data is assimilated into the model to try to generate as accurate a complete picture of the global atmosphere or ocean, depending on which model you're doing, or maybe it's a coupled model that you can. So just a little cartoon of DA. The general idea is that I have a model, I have an observation of that. So this is actually a particular sea ice model. The picture here comes from Deborah Sulsky. She has a nice elastic decohesive model with fun rheology. This is just the general momentum equation typically for sea ice. This is just a satellite image of sea ice. And the idea is we want to try to, whatever we're modeling and whatever data we have, we use a data assimilation scheme, of which there are many, to try to combine these two to estimate the truth. And the fact is the models are imperfect. The data is imperfect. There's a lot of error in the data. We can't trust either 100%. So this combination is really the best way to get an accurate assessment of what's going on. So just in general, the better these three things are, the more this thing can actually look like truth. But just sort of also an aside, data assimilation can provide other things as well, typically what's called a reanalysis. So we have 30 years of satellite data and many more data sets dating back even further than that, which can tell us a lot about the state of the planet, but it's in little snapshots, right? Little swaths of satellite, and it's hard to generate a complete picture of what might be going on. But what we can do instead is initialize a model in the past and assimilate data all the way through to generate a more complete picture of the planet's recent past. And this is an example of a reanalysis done by ECMWF that generally shows increasing temperatures over time globally and what those anomalies might look like. And it's a combination of those models and the data that's available. Okay, so that's a very brief introduction to what data assimilation is. I think this is worth looking at if you want to explore sort of what these global models do and the kinds of data that they that they take in. This website is absolutely fantastic. And I think it's worth just looking at because it's also cool and fun. So WINDY pulls information from various global atmospheric models and ocean models, et cetera, as to sort of a general snapshot of the state of the planet. It also makes available visualizations of various data that's used. But for example, right now, this is wind at the surface of the Earth. ECMWF is the model that's run by the European Center for Medium Weather Forecasting. GFS is a US model. I can switch to that and see what it's saying. You notice a slight difference between the two. ICON is a German model. There's a slight difference there, but you can explore the various models. Zoom in, zoom around. Let's see, I think I've got the video over this bit here. But you can also move up through various layers of the atmosphere, right, to show you the scope of what these models are doing. They're really trying to copy everything, get a sense for the winds. You can look at rain and thunder, clouds. You can even just look at radar and satellite data if you want. So let's look at weather radar. So you can play around and look at the weather radar. These are the kinds of things that get assimilated. Just a satellite picture of the Earth. So it can be a lot of fun to explore. You can look at these, you can move up and down through the atmosphere. There's a whole bunch here, and I would encourage you to do it. It's kind of fun. Let's see, so.
Do they offer polar projections so you can see what's happening around the poles?
No, that's a lot harder to do, like in terms of sea ice, or you just mean general wind patterns and rain, et cetera? I mean, you do get a picture, but it's not, so like you're asking, can you look at it down from the top down? No, I don't think there is anything like that. Yeah. Yeah, it's sort of this sort of Mercator projection visualization that they have. But it's nice. And you can, of course, push play down here to sort of see how things might evolve in time. I think there's remnants of the recent hurricane in Florida here moving around. But during hurricane season, this can be an interesting place to check to try to see what's going to happen. So anyway, I think it's cool. I think it also shows the scope of what these models do. And yeah, it can be a lot of fun to play around with. So I'll stop playing with my favorite little website. But I think it's worth looking at. So how do they put all of this stuff together? So let me talk just a little bit more about DA in general. Let's see. So we'll go back to the slides. There's many methods in data assimilation. This is just a few of them. Some key terms that are worth knowing. I'll give a cartoon of H, but the observation operator. This is an important piece of DA. It takes model space to observation space. So for example, this could be the amount of sea ice at the poles. But what's really observed for those is typically not actually the amount of sea ice, it's a microwave emissivity of the ice. So an observation operator could, for example, take the ice you have in your model and run its microwave emissivity all the way up through the atmosphere to see what the satellite might see at the top. It could also just be as simple as a projection matrix that kicks out variables that aren't observed. So it takes lots of forms, but that's the key, is that it takes model space to observation space. B, we'll see this a lot. This is the background or error covariance matrix. These are all the error covariances between all of the variables in your model. So if it's an atmospheric model, it might be pressure, temperature, humidity, but how those things vary together. This is a very important thing and often very difficult to estimate. And then R is an observation error covariance. So this depends on what observations you have, but how those will vary together as well. So typically, now that we know what those things are, the general idea is we have some model. In this case, think of it as a matrix A times some state X. And we will refer to this quite a bit. X is a state vector. So if you imagine your copy of the planet, what you do is you take every single point and every variable for those points and arrange them into one very, very, very long vector. You do all the DA in that context, right? So we call that the state vector. So it contains everything, all the variables at all of the model points. but we have some model that forecasts it forward in time. So one very popular form of data assimilation is called optimal interpolation. This is also called the Kalman filter. It's fun to derive, but essentially we have a forecast, we have a Kalman gain matrix, which is really defined in terms of these error covariances and the observation operator itself. And then we have a difference between the observed quantity, Y0, and H times your forecast. So remember, this is taking you to observation space. So this is really the difference in observation space between your model and what's observed. Weighted by the Kalman gain, added to your forecast gives you what's called the analysis, your best estimate of the truth. There's a lot of work on trying to estimate these. You can do them with trying to estimate K. You can do it with ensembles, lots of studies, but typically this is a very popular and computationally cheap method to use. There's variational methods. 3D var is 3D variational. This is just minimizing a cost function J that compares your forecast. We're trying to find the best X that minimizes this. So we've got the background error covariance, and then we have our observation. So this, you can think of this Y here would also be H of X, but it's 3D in that we only do it at one time, right? So we have one observation, one forecast, and then we minimize this cost function to find the optimal X. And then there's 4D var, which I'll talk about in more detail today. If you notice, the difference between these two cost functions is now I have a sum of these moving through time. So I'm considering observations in a time window as opposed to at just one time, and finding typically, usually, an initial condition, the X that we'll optimize for is an initial condition such that when we forward the model, we're consistent with all of those observations. Whereas 3D var is just an abrupt addition to move you a little bit more toward the observations based on how much you believe your model and how much you believe the ops. Just a fun fact, you can also just do Bayesian statistics. What's the probability of my system state X given my observations? But if you make a Gaussian assumption that this distribution is Gaussian and you do a maximum likelihood analysis, you actually just end up with optimal interpolation. And the same is true, the solution to 3D var here, under those assumptions, you also get just the Kalman filter as your best answer for X. So they all correspond to each other nicely when things are Gaussian, which they usually aren't. Okay. So that's just a quick overview. This is a cartoon of H, just because it is such a weird thing. I like to show this so it's in the back of people's minds, but sea ice as an example. Again, you don't actually, I mean, you can get visual pictures, but usually the Arctic is very cloudy. You don't have any optical imagery to estimate ice percentages for concentration, but you do have microwave emissivity, and you know the emissivity of water, you know the emissivity of ice, and you measure at the top of the atmosphere an intensity of light, of microwave light at various polarizations and frequencies. And from there, you try to back out how much ice produced that. But it can be very tricky. You could have melt ponds on top of the ice, which is just freshwater ponds that form when the snow begins to melt as you move into the spring, or you might have just ice and open water. But these two look very similar to the satellite. So there's a lot of interesting, fun problems in trying to deal with observation operators. But this is the idea. An observation operator takes you from model space to observation space. Sometimes simple, sometimes not simple at all. Okay. Here's just a cartoon of sequential DA with a Kalman filter, just to give you a sense of how that works. This is not 4D var, but I'll give you a cartoon of that as well. But the idea is that you have an initial background, an initial guess. You forward this with your model. You get your error covariance. You take your forecast, your observations all together. You update that, in this case with a Kalman filter. You get an analysis. And then you do that again. You forecast, you take the observations and the error covariances you have, you perform the DA step, and you do it again. This would be nice if this worked really well for the weather models, for the global models. It's computationally inexpensive, it's relatively easy, but it typically does not produce the best forecast for the longest period of time. So what does better is 4D var. So just to pick apart the cost function here a little bit, so that we know what we're dealing with. Let's see if I can move the little videos here. So the general idea with 4D var is that we want to find an optimal initial condition. So this would be like initializing the planet with the temperatures everywhere and the pressures everywhere, such that when we run from that, we're consistent with observations. So the cost function here will minimize this cost function with respect to an initial condition. XB is like our first guess initial condition. It's what we're starting with here. It's our background. B is that error covariance matrix. There's lots of ways to estimate this. We'll have observations over various times. So here I'm adding up these inner product terms. Whoops, sorry. Adding up these inner product terms for each discrete time in a window. I'll show you a cartoon of this. But H here, these are observation operators. This is a model operator. So this is forwarding the model from the initial condition, from time 0 to time, I guess I should have used I here, but from time, well, yeah, to time ti.
How do you decide what window to take in time? What are criteria for that?
Yeah, it depends on the model, the number of observations you have. And it depends on the type of 4D var that you're doing. There's strong constraint and weak constraint. Strong constraint essentially assumes a perfect model. You would want a shorter time for that. Weak constraint allows for some model error. You can have a longer time window to assimilate. So yeah, it depends on several things. What the general rule of thumb for the giant models is, I'm not so sure. I'm more on the algorithm development side.
Do you have some notion of stability of your solution? You know, so if it's too long, it's too unstable, and you know, optimize it in some such way.
Yeah.
No, forward in time, people think of Lyapunov horizon. You know how much you can see, but now you're in space-time, which is much better than forward in time.
Right. Yeah. In general, I mean, for these large weather models, forecasts are typically very good for 3 days out. They degrade a week out, and then after 10 days, you wouldn't believe it at all. The assimilation.
So is your window 3 days, 5 days? Now that we are talking real time units.
I think it depends. I'm not sure exactly what ECMWF does or GFS does, but typically these assimilations are done every 6 hours as they come in. I would think probably with 3-hour windows, but I'm not 100% sure. But there's a lot of tuning and other things that go into these, but yeah. But I imagine it's a little bit different, and it may depend on the windows may depend on the observations that are available as well. So I would imagine it's quite a complex set of code that decides windows for various satellites and what's available and when and where. And yeah, but that's interesting actually to think about, because it does get quite complex, I think. But in terms of just doing the 4D var, if we allow our window to be delta t, just from t0 to tn for any generalized model, these are the pieces that we put together. So you can see we're really just sort of trying to consider each observation. This matrix R tells us about the errors with the observations at each time. B is telling us about the error of the model. And we go and we try to find this initial condition. So the simple cartoon for this is the following. So this might be our time window from t0 to tn. In general, what happens is we make a first guess forecast. We initialize from our best guess. We run the thing. We'll get observations over that time window. And based on those observations, we minimize the 4D var cost function to obtain our best estimate of, and remember, there's error with the obs, so we don't necessarily want to perfectly fit them, but we get an initial condition for which, when we run, we're relatively consistent with the observations. And then what we would call our forecast after that would be whatever comes after the time window. So this might have been the previous forecast, of course, this cartoon, and then the corrected forecast that we might get. And I think that one of the advantages for 4D VAR is that you really consider a good chunk of the past before making a forecast. And given how chaotic weather can be, the difference between rain or not can be sort of a critical threshold. Trying to include all that information, I think, is
can I think of it? It's slightly different, but you're phrasing it. I have a window, and I'm using this window to optimize my prediction within the window. So it doesn't actually matter what my X0 is, it'll just come out. But what really matters is that I have a range of an interval of predictions, and then I shift that window forward in time and improve it or fix it. And that's much better than just improving, one step in time. That's much more robust. Is that a way to think of it, or am I wrong?
Yes, you can think of it that way. And I should say there are different flavors of 4D VAR. You don't just have to find an initial condition. You might find several initial conditions in your window, depending on how long it is. But yes, I mean, yeah. So we're the thing that we're optimizing for, at least in this sort of example, is an initial condition. But in finding that you would have used your entire forecast, and you actually do it iteratively, so you'll often reforecast in what's called the outer loop, which I'll give steps for what typically a 4D VAR is. But yes, I think you could think of it that way. Mm-hmm. But typically what we're looking for is that initial condition, but it's one that gives you this optimal forecast over that time window. Mm-hmm. Okay. Okay, so let's see. Okay, so if the goal is to minimize a cost function, we have to minimize the cost function. So this is typically done with just a steepest descent algorithm. So that means we have gradients to calculate. Given the size of the system, we don't just want to try estimating it with finite differences or something like this. It's very large. It has to be computationally tractable, which is a challenge. So there is an efficient way to do it that does make 4D VAR practical for these large models. And that's through this idea of a tangent linear model, which is often abbreviated as just TLM. What the TLM does, or how it's found, is by linearizing around some nonlinear trajectory from some time t-1 to ti. So that is to say, if I take a perturbation at time ti-1 with state x, and if I were to apply my nonlinear model to that, it would evolve to x at ti plus some small perturbation. That, looking at this, expanding this out as a Taylor series, essentially, I have my model at x of t, and then I have the derivative, really, of that model times this increment at ti-1. This L is what we would call the tangent linear model. And this goes into calculating the gradient of J in a computationally efficient way. But essentially, you can just say the TLM, for all intents and purposes, evolves an increment, a small model increment of the state vector forward in time. So we would say that's the tangent linear model. If we have a tangent linear model, we can start manipulating the cost function. Oh, I guess first I should also just point out that if I want to evolve an increment from time ti to time tj, and I have smaller subwindows over where I'm doing it. So imagine this is the larger window, and then I have those series of observation times. The tangent linear model from the beginning of the window to the end of the window, or some other sub piece of that, can be put together as a product of the tangent linears, taking you from earlier times all the way through, right? That's an important point. So if we have this, and we have this established relationship, then in order to minimize this, I'm just going to take a derivative with respect to x naught. So I'm just throwing out an operator there. If we make use of the fact that for a symmetric matrix A, if I have vector transpose matrix vector with asymmetric, and I want to take its derivative with respect to something, this will just give me 2, if x is a function of z here, think of it that way, but 2 times the derivative of that vector. I left off some vector arrows, but with respect to z times ax. So if I get to use this without proving it, when we take the derivative, we get exactly the same relationship. So here I'm taking the derivative of this inside term. So y does not depend on x, not at all. It's just the observation, right? So it's gone. So I'm taking the derivative of this, transpose R inverse, and then I've got this guy sitting here. This is H of model of x naught. So a chain rule gives me this. And then just rewriting this as an H prime, that this is now a linearized version of the observation operator. And then recalling that the derivative of my model from time 0 to ti, where I'm summing up those times, would be this tangent linear, right? So this product, basically, depending on where I'm at, how many of them will be there. And then this is a transpose, so just apply the transpose, right, to this. And I end up with this relationship. This is maybe an easier derivative to take, but this is just the background term. But all the focus is on this observational piece. So this is then our gradient in terms of the tangent linear model. So dragging that over here, just taking a look at this, and the reason I'm setting this up is to set up how important the tangent linear and what's called the adjoint are for 4D var. But if we just examine this transpose term and apply it to the product we were looking at, we just noticed that the order in which they were applied is reversed. So instead of going from time 0 to time 1 to time 2, applying it to the increment, now it looks like we're going from time I with an operator I minus 1 to the next time down, so going backward in time with transposes of those models, which could be rewritten with L being our tangent linears, but now instead of going from T0, say, to Ti in this notation, from Ti to T0. So you're stepping these increments backward in time with this term. Whoops. Let's see. Hit the mouse too many times. Okay. So this object here is often is referred to, I shouldn't say often, is referred to as the adjoint model. And like I said, it has the effect of moving these increments backward in time. So I'm sorry, this is a lot of sort of factorization, but it makes the point of how important TLMs and adjoints are to 4D var. But if we then take this remaining piece here that we have that isn't the adjoint, and just call it D at TI so that it's a little nicer to look at, we can refactor this a little bit, just multiply, collect parentheses, etc., so that we get a form for the gradient of our cost function as such. This just makes it a little bit more efficient calculation. With big models, these things have to be considered. Here we'd apply the adjoint n minus 2 times, but if we rewrite it this way, we cut out some of that excess multiplication. Okay, so once we have the gradient and an efficient form for the gradient, then we can do 4D var. So this is the general 4D var recipe. So first, we integrate our nonlinear model forward in time over our window, and we save the model state at each observational time step. Using the observation operator and our observations, we calculate these weighted observation increments, those Ds, right? So I would have my nonlinear model at each time. I'll take H of that to put it into the observation space. I get a difference. I hit it with the covariance matrix and then the linearized observation operator. And I calculate one of these at each time. Then essentially I use the adjoint model to advance this thing. You can think of it this way, advancing this vector, which is sometimes referred to as the adjoint variable, backward in time to t equals 0. Right? And they sort of build up, but the equation advances it backward in time. But essentially I'm just calculating this gradient. I get the Ds from the nonlinear model. I have the Ls from the tangent linear model, taking their transposes to get the adjoint, and I get the gradient. Once I have the gradient, I do a steepest descent. I adjust my initial condition, and then typically we go to another outer loop and we rerun the nonlinear model, and we play exactly the same game until we get to some convergence, which is ideally the gradient is very close to 0, right? Things aren't changing anymore. And that's the general recipe for 4D var. The thing that makes it practical for these very large models, whoops, I tried to highlight that, but that turned into a click, but is this tangent linear model and adjoint formulation. And that's why they're so important. In the sort of very brief derivation I did of this, the TLM and adjoint here are matrices, but in these large codes, a large weather model, yes, it has a series of PDEs that advect winds and pressures and temperatures and other things, but there's a lot of very complicated parameterizations at the subgrid scale. So we have two sort of things for an atmospheric model. One is the model dynamics. This is mean motions of the atmosphere. Calculating the TLM for that part of the model is typically pretty easy. It's like taking a derivative. You can get a nice matrix for that. But then there's the model physics, as it's often referred to, but these are processes at smaller scales, various cloud physics, precipitation, how aerosols behave, all sorts of things that in code are not just simple equations that we can take derivatives of. They may have if statements and cases and other things that aren't typically thought of as I can hit this with d by dx, right? Which causes difficulty in coding TLMs and even more so in adjoints. But this is just an overly simplified diagram of how some of these models work, but typically we advect the atmosphere with the dynamics, the mean motions, we solve and update all the physical parameters in the subgrids. Those then will affect things like pressure, temperature. So we advect again, and it's sort of like this two-cycle thing. So the trick is when we realize that that's the case, if we think about what the TLM is doing, a TLM advancement, really we're applying linearized dynamics forward, and then we're applying the linearized physics to that as well. This part can be tricky because taking a derivative of some very complicated code with lots of tricks to understand how aerosols behave and you know, if statements, catch statements, other things that optimize memory, who knows, but it can be a difficult thing. So somehow that has to be figured out so that what the TLM itself is doing, even if it's not a matrix and it's just a subroutine, what it does is move an increment forward in time as the model would. An adjoint advancement is kind of the opposite. We're going backward in time. So here, as we applied linearized dynamics and then linearized physics, now we need to undo the linearized physics and then apply the linear dynamics backward. And again, this can be very time intensive to code for these very complicated models. Excuse me, but it is certainly doable, but it leads to a problem. So if you want to update your model physics, there's a new advancement in cloud physics modeling or aerosol modeling. If you want to continue to do 4D VAR, you have to update your TLM and your adjoint. And this can take many, many man hours. And there's a lot that goes into that and restructuring it just so that you can do it. Almost to the point where sometimes you think, well, why should I do 4D VAR? But then, well, it gives you the best prediction. So it becomes worth your effort. So it would be nice if we had a different way to get tangent linears and adjoints, because that's what makes 4D VAR practical, so that we can keep on top of these things as model advances happen, or as model resolution changes even. Just being able to do something a little different to get the same object that we need to do 4D VAR. So this is where the idea of a hybrid tangent linear comes in, but I think to understand a hybrid tangent linear, it's worth understanding something called a localized ensemble tangent linear, which does not really take any derivatives at all. It's more just a way to learn a matrix that acts like the tangent linear and approximate it. So if we go back to one of the definitions for a tangent linear that we had, it just advances a model increment from one time to the next, right? That's what it does. Instead of calculating that, we play a game where we try to learn that. So if we think of the jth element of the state vector, just pick one, but remember the state vector contains everything the model has to offer. But if we take one element of that at a specific time, and we make the supposition that this depends on other model increments at a previous time, so a list of them, the ones that would quote unquote influence this one forward in time. So say there's S of them, right? Just list them out at the previous time. We might write an equation as follows, which is that for this one variable at this one grid point, it's some vector times all of the other increments in that vector that had an influence on it at the previous time. Right? So this is just setting up an equation to solve for this mu j, right? Where we would think of mu j, in this case, the values there would correspond to all of the non-zero values in the tangent linear, right? Which maybe is clear. This is a matrix, right? If it's going to evolve this one increment, there's some row multiplying the vector, right? These would be the other pieces of the vector at the previous time, right? So this, if we can find this, we're just finding the non-zero values in the tangent linear matrix. This is not a well-posed problem, right? So we need to do something about that. And in this case, what we do is we use an ensemble to basically set up a least squares problem to solve for that vector. And I should say this thing that we're, maybe before going on, this, oh no, I have a picture, but we would call this list, the influence region for that grid point and variable of the model. And for an LETLM, a localized ensemble TLM, that's typically something spherical. It's points around it if you were to think of it in 3D space. For the hybrid TLM, what makes that tractable, because this really isn't tractable for a large model, is that we would actually only do that on columns. And I'll explain why, but anyway, the general idea is the following. So we take an ensemble of nonlinear model runs, right? So in bold, I've put things that are coming from full nonlinear models, right? We look at what those increments are at that time for each ensemble member. And then we take our mu and we use a matrix where we take the influence region for the particular point that we're looking at, and we just list those in columns, right? So here's this influence region, and I do one of those for each ensemble member. Right? And then I'm going to use this to estimate that column of the TLM. Okay, so in a more compact form, right? Just a vector, and then we might say we have this matrix of increments. Okay, so if that's our problem, so yeah, this is just a cartoon of forming that matrix. It's one that's specific to what we were doing in JEDI with this, but imagine if your model, very, very simple version of this, imagine if your model has 16 grid points and 2 layers, 2 atmospheric layers, and 16 grid points at each layer. The matrix, that delta X that we would form, say for this grid point, so the one in red is this, these are 2 ensemble members, but the one in red is for that grid point. It'll have a specific influence region. In this case, it's just everything above it and itself, right? We just take those and we throw them into the matrix. So there's one for this ensemble member, and there's one for that ensemble member, and then I have n of those, right? But the influence region could be different. If we expanded it out to these others, they would just line up in that matrix. Does that kind of make sense? It's a simple picture, but I think worth showing. So, okay. So then with that form, then we can just solve this as a least squares problem. So I find the normal equations, I multiply by delta X transpose, and then I find the pseudo inverse. And now I have an estimate, call it mu hat, for for the non-zero values in that matrix. So I could do this then for each and every grid point and variable, and then I'm piecing together L, the tangent linear. Okay. One nice thing that is at least nice to know is that if you have a large enough ensemble and S is large enough so that you're actually getting the exact influence region, right? In the limit as that increment goes to 0, you're getting the exact tangent linear. So there is some limiting behavior that tells you that under certain circumstances, this could be exact, which is always a reassuring thing to have, okay? But in practice, if you wanted to do it this way with just a localized ensemble tangent linear, it's going to be intractable. You need such a large ensemble, and the influence region, think about how many points we are with the planet. It's also typically very large. It's too computationally expensive. So this is where the idea of a hybrid tangent linear model comes in. And this is work coming from someone named Tim Payne, who's at the Met Office in the UK, who we work very closely with. The Met Office in general, JCSDA works closely with, who developed this idea. But the idea is that for most models, we have some kind of tangent linear. It may not be complete. Maybe new physics was added and that hasn't been put in yet. Or maybe we're just doing the dynamics part. If you recall, I mentioned that for the dynamics, that's actually fairly easy to calculate and code up. That part's, it's the physics that's difficult. But we have some version, an approximate tangent linear model for our model. The HTLM takes advantage of that. It combines that with localized ensemble tangent linear model methodology, I guess I could say. So the general idea is that suppose we have a simplified TLM, which I can refer to as just, go back, the STLM, but that's whatever rough tangent linear model you have. In order to build a better tangent linear, what we do is we take the simplified one, call that M here. We use that to forward an increment in time. So I go from I-1 to time I, but I put a little minus here, which is saying this is the one done by the poor tangent linear model, the incomplete tangent linear. Then we use the ensemble method to find a matrix that would then update that rough estimate of what the increment should be at the new time to a better estimate using the nonlinear ensemble. So the idea here is that you get sort of the easy pieces of moving this forward in time. And even though you were missing physics, you're using information from the full nonlinear model, which has everything in there, to then correct your increment. So the general problem that you then solve is very similar, right? It's just like the LETLM, but instead of putting in values at the previous time, I'm just putting in the values that I move forward with the TLM into my matrix. That's the only difference. So I go a little bit with the rough TLM, and I do that with the ensemble. So I have to move each ensemble with the TLM, and I take those, and then I form my matrix. Okay. So if we found N, we'd have the update, but there's a slightly nicer form that we use. So we can think of it as, if I have this N, I'm taking my rough estimate from the bad TLM and I'm updating it with this matrix. And this is the full vector here to get a better estimate of the increment state vector at time ti. If you break it down to be written grid point by grid point, you can write it this way. So this is J, this is one part of that state vector at time ti. So the corrected update is the previous one plus what we call the HTLM coefficient, but it's just a vector C here, times the influence region for that particular grid point. So this would be actually just the influence region. So if we can calculate these C's, we can update each grid point after we use the TLM. And in a very similar way, the adjoint, right? Which is really what we need to move these increments around to do our 4D bar. So Xi, the solution for Xi looks like this. Lambda here is just a regularization. It's optional, but typically regularization is useful in numerical problems like this. But just solving the same sort of least squares problem, we can get Xi for each grid point. This delta E is where all the information from the nonlinear ensemble comes from. So here's the nonlinear ensemble in bold, and then what the TLM would tell you you should have been at that time, but these are coming from the full nonlinear model, so that difference goes in there. If we calculate all those coefficients and we put them into a matrix, this just gives a nicer form to see how we get the adjoint from this. Right? So I just put them on the diagonal. This would be an n-dimensional state vector. Then once I have those, using the TLM, and I'll talk about how they get calculated, but then to use an HTLM, your TLM forwarding goes in 2 steps. First, I use the simplified TLM to move from previous time to the next time. And then I update that with my coefficients, which I would have pre-calculated. I would have these pre-calculated, and I update that. So it's 2 steps, simple and then correct. Then for the adjoint, it's sort of the reverse. I would start at if you think of it as going backwards, starting at the updated one. Now I've taken a transpose, which in this case is just the adjoint of that matrix. I apply that to that vector, so I'm unupdating in a sense, and then I move backward in time with the adjoint of the tangent linear. So they just get 1 extra step for each one. But you need these things for all the various 4D bar algorithms. So, but the idea is that once you have those coefficients calculated, you now have this sort of corrective procedure you can use. Okay, so we need those coefficients. So how do we calculate those? The sequence to do it essentially is using your bad TLM and updating it as you go. So we initialize our forward ensemble of whatever size of the full nonlinear model. You store those state values at each observation time that you'll have in your 4D bar window. You initialize an increment ensemble from a control run and the differences between those of your nonlinear ensemble. So now you'll have an increment ensemble. You use the tangent linear model, say from time 0 to time 1, the STLM, I should say the simplified one, to go from time 0 to time 1. Then you form all of those matrices with the influence regions, calculate the C coefficients at that time, then use those same coefficients to update your increments forward next time with your STLM, get your matrices, calculate coefficients, update those all the way to the end of the window, and you save the coefficients at each step. And then once you've done that, you now have the list of coefficients for your 4D var window. Then if you wanted to do 4D var, you would just take that with you, initialize another model run, and then use those coefficients to update in a regular 4D var scheme with those 2 steps, right? So the difference between an HTLM run, if you were using a regular TLM, it's just 1 here, and a regular adjoint's just 2, but these other update steps come in, but you would just pre-calculate those coefficients. Okay, so that's the general idea. So if you're interested in, I guess I should say, yeah, but if you're interested in learning more about that, there's a paper that I'll show to reference here at the end. But Tim Payne at JCSDA, we've just coded one up and we're testing it with the quasi-geostrophic model, a multi-layer version of that. We've added some nonlinear physics to play around with, but we'll see how it plays out. We're just getting to that point, but we've now implemented one. But there is some work using the model at the Met Office showing that the hybrid TLM does tend to outperform using a bad tangent linear and is tractable. And the Met Office is interested in actually making this an operational formulation for their 4D var system. That said, there's possibly all sorts of other hybrids people could use. And I think DA is kind of a dirty science. It's not always mathematically perfect. But what you're trying to do is get good forecasts. Just 2 examples that I think are kind of fun. There's something called a physically informed neural net. In this case, you would train your TLM on data, but you would also be able to plug in the equations that come from taking the derivative of dynamics, and you include that in the loss function that you use to train the network, so that the network is considering sort of a set of governing physical laws that it should be obeying when it learns to make predictions. These kinds of things are interesting in terms of getting rapid TLMs and adjoints out. There's also something called an echo state network, which essentially has a bunch of random weights. You throw inputs into this, and it gives you some kind of output, which you then have a filter layer that you do a linear regression on to relate that output to what you know the answer should be. So you train another filter. But these have successes being quickly and cheaply trained. And in some cases for pretty chaotic equations like Kuramoto-Shibashinsky, people have gotten 8 Lyapunov times out of these things, which is kind of, I think, interesting. But in principle, you could try to get a tangent linear and adjoint these ways as well. But that's, far off, I think, sort of things that we would be doing. But I just like to mention it. So then just to close out, I'm just going to plug JEDI. So JEDI is the Joint Effort for Data Assimilation Integration. It is meant to relate to Star Wars. There's a lot of repository names. At JCSDA, we have Vader, R2-D2, Ewok. We do our best to keep that standard going. But the main goal of the JEDI project is to create a general DA system that anybody who wants to can use. For the most part, all of these DA methods are model agnostic in that we're just taking model states and data and combining them to get an estimate. There's no reason that NASA and NOAA and the Met Office should all write an HTLM for themselves when it could be written in one place and they can all use it. So that's sort of the general, not just HTLM focus, but that's the general goal of JEDI, is to avoid reproducing developments in data assimilation, observation filtering, anything that is relevant to these sorts of things. It's also aimed at producing rapid new developments because everybody is working on the same project and it all goes into the same thing. And by following a specific set of guidelines, everybody can use it. There's interfaces between your model and JEDI, but that allows you to use the system. So that's sort of the core mission, is to really produce something kind of like ECMWF has, where they've got all the European countries collaborating on one system, and they have honestly the best forecast skill on the planet at the moment. This picture I just included because it's kind of fun. It's generated by an AI algorithm where you give a description, and at a week-long relaunch thing that we had at JCSDA, we had a contest to get something to hang. So eventually this will be hanging in JCSDA. It's just a Jedi Knight with a lightsaber looking at the Flatiron, a thunderstorm over the Flatirons in Colorado. I just think oh, and I like that they added oil painting by Monet, and the AI sort of seemed to pick up on that. So I thought that was very fun. So that's generally what JEDI is. This is just kind of an example of the generality of the code. This doesn't have to make sense, but there's this, most of it's in C++. There's interfaces with Fortran, and you can use that. But it's kind of interesting to point out this template type name model, right? So the idea here is that you'll implement certain things. So say for QG, you write a TLM, you write something called a state, other things that are needed for JEDI, and those interface with the JEDI system for your model. But the idea is any model, bring your model, we'll do the DA for you, right? And we'll have advanced algorithms that you can use and are well tested. That's the goal. So why would anybody else be, oh yeah, please go ahead.
Christian, this gives me creeps because I'm afraid of having a universal straitjacket. So I love the idea that all data is accessible to all in a universal format, which is a lossless format in a sense that no prejudice, modeling prejudices are in the data. Mm-hmm. But if you have a totally different idea than 99% of other people, currently we have a competition model. So somebody in India can do a crazy weather prediction model, very different from anybody else. I'm just afraid that JEDI will kill any original thinking, and it'll make us all in a bunch of ants. So this is the fear.
Yeah. So the idea is that the reason you might want to use JEDI is for what's available. But if you do have the crazy idea, it's an open source set of code. So you can petition to add it into JEDI. And what that does is there are certain classes in JEDI, things called state writer, increment, tangent linear model, that it itself is not a tangent linear model, but given what you write on your model side, initializes it to then run with a variational scheme, a 40 var week constraint, will just run with that. So if you had a crazy idea for a tangent linear model, you can implement it. And then if you write the interfaces to JEDI, you then don't have to write the minimization algorithms. You can use them. And then if you want, if you're excited about it, probably JEDI would, JCSDA will be interested in including it, but you can submit a PR to GitHub And the idea is, yeah, we want to pull these crazy ideas in, but also provide a platform where you don't have to reproduce the things that you don't have to reproduce, that aren't new and are irrelevant. And really the way that I think this will end up working with the partner agencies, they'll all have their own versions of JEDI. And then there'll be the core JCSDA version, and hopefully they don't stray too far from each other. But the idea is take what you want, use what you want that's useful, and add. Yeah. So hopefully that.
Sorry, I have to go to the next seminar.
Okay. Yeah.
I just want to say the following. Please don't stop because of me. I totally agree with much of what you say. I would just like to think not as moving forward in time, but optimizing the book of admissible kinds of weather, which is meaning, if you wish, videos of weather which have some future and some past in all of them. I'll send you an email, but anyway,
Okay.
I think it'll be much more robust than thinking forward in time. That's just not a good way to think about turbulence. Bye.
Yeah, I'll be interested. Yeah, thanks. Okay. Yeah. Okay. Yeah. So I'll quickly just try to wrap up. There's not much more to say, but so yeah, people interested in JEDI are typically large agencies doing weather modeling, but I think I'm talking to math students, right? So why would you care? Because you get to do math if you want. I'm a mathematician. I'm interested in the algorithms. I like applied math. I like working on something that's relevant. And as we were saying, yeah, anyone can contribute to this project. There's a bit of a learning curve getting to use JEDI, but there are tutorials, etc. But there's a lot of fun linear algebra. Forward-looking, we're really interested in bringing in machine learning. So if you have interests in that, there's avenues to use, real big satellite data, real big models, and play with this kind of development if you're interested in sort of that computational side of things. So I would say, yeah, keep it in mind if it is something that you're interested. There's small pieces like algorithms that are just perfect for mathematicians. So yeah, with that, I'll just say thanks. This is the paper with the hybrid differential ensemble linear forecast model. I call it the HTLM. I think it's pretty well written. It's a good read. If you're interested to poke around JEDI, github.com, JCSDA, all the repositories are there. JCSDA.org/projects shows what else is going on other than JEDI. There's the community radiative transfer model. There's observation ingest, a whole bunch of Skylab, a whole bunch of other things that might be interesting. And I do want to mention this because I think there are students here. So it hasn't been done recently in the past, but we'll be spinning this back up, what we call JEDI Academies, which had been remote during the pandemic, but I think maybe more in person. So hosted at Boulder, et cetera, where you'll come for a couple of weeks to learn about data assimilation, to learn about the JEDI system, to get familiar with it, just as an experience. So we'll probably announce that soonish in the next couple months when those would be. So keep an eye out. And if so, I know that Emmanuel, you're working with some students in particular, so I'll send you emails, as these things happen, but just to bring it up. And then, yeah, and then this last AI art image, right now there's a code sprint on Vader, which is the variable derivation repository for variable changes between models, uses recipes to switch between models. So the director had typed in Darth Vader dancing, developing recipes in the kitchen and sent that out on Slack, but I thought it was kind of fun. So, okay, that's all I've got. Thanks.
All right. Thank you again, Christian. All right. Everyone, let's thank Christian for this wonderful talk. Okay, at this time, is anyone